Greetings and welcome to another EMBlock screencast. In this screencast we're going to look at how Solidity handles call data and how we can make use of that in Yaw as well. So let's take a look first of all at some theory and then we'll practice some ideas. So first of all, let me just clear this out here. We want to just understand how call data works in the context of Solidity. So I've got a contract here called Yaw call data, and it's empty at the moment. Now, the way that call data works is that when you send a transaction to a smart contract, it's expected by Solidity that the first 4 bytes of that call data represent the function signature that you want to invoke. And we'll see in a bit how we can generate that. Now, Solidity then expects, if there are parameters, for those parameters to be grouped together in 32-byte increments following the 4 bytes of the function signature. Again, we'll take a look at that in the console. Now, if you send more data than Solidity expects, then Solidity will just simply ignore the trailing call data. So if you send, say, 32 bytes of data, but the function signature expects only 1 byte, then 31 bytes will just be dropped off and not used. Now, it's possible, of course, in Yaw to break the convention and write functions that take any manner of size of data because there's no restrictions and there's no standardization that's being monitored through a compiler such as Solidity. So you have more flexibility with Yaw to break these conventions. But let's take a look at, first of all, how you can generate a function signature. There are many ways of doing this. I'm going to use cast. So I've got here open cast. Well, I've got terminal open, and cast is a utility from Foundry. So in order to generate a function signature using cast, we can just pass in the string of the interface of the function that we want to use. So we can see here balance of address, which is a standard ERC20 function that we probably all know very well, generates this function signature 70A08231. Now I've got the Yaw docs open, and if I search for that, you can see here that in this example, the complete ERC20 example that's written in pure Yaw, by the way, so take a look at that if you're interested, shows that the function signature of this function is indeed what we just generated in the terminal there. So that's the function signature. Now, how about the data that follows that? Well, balance of is expecting an address, and in cast we can use call data. So let's try that out. We can use call data, and we can use the same function signature, balance of, and then we can pass in an address here. Now, it's not going to work like that because I haven't passed in a valid type or a valid data type for address. So let's use cast wallet new to generate a new address. It just generates a random address. And we'll come back here and we'll run this again, but this time we'll pass in a properly formatted address. Okay, so now we can see that we get the full call data. So actually what we have here now is a piece of data, call data, that we can send as a transaction to a contract, to a smart contract that has this function defined within it, and it will invoke that function and pass in this address data. Now I want to open up Sublime and just show you. Now let's have a look in Sublime and see how this is broken down. So we've got the 4 bytes of the address signature, so that's 4 bytes. And then we've got the data, which is this. Now, as you notice, it's 64 characters long, which is 32 bytes. Okay, so that's what Solidity is expecting. So you notice that what it's done, really, the call data formatting, has taken the address, which is 20 bytes long, and it's padded the zeros to the left of it to bring it up to 32 bytes. And that's just in line with the standard of the Solidity ABI for call data specifications. Right. So let's take a look at another quick example here. Let's clear this out and let's try cast SI. And this time let's have balance of address, and we'll also include a uint 256. Now notice we don't have any spaces here or any parameter names. We just include the bare bones interface. And now we get this other value back, which is the function signature for this particular function. So now we can try this again. Let's do cast call data, and we'll use the same function, but now we need to pass in two parameters. We need an address and we need a uint. So let's get the same address as before, and let's just pass in a uint of 1. Okay, now what's went wrong there is that we don't use commas in cast. So let's do that. And you can see here that we've now got the call data, which is now slightly longer. But hopefully you can see without even having to break this down, that this is the function signature followed by the address with padded zeros, so that part, followed by the number 1 with padded zeros to bring it up to 32 bytes. So we can drop this into our editor here. Actually, just put it below that, and we can see here the 4 bytes followed by the address followed by the 1 right after it. All right, so that represents this interface here, balance of address and uint 256. So how can we generate this call data in Solidity? Well, the answer is to use ABI encoding, or ABI encode with signature would be one way of doing it. So I can show this in another tool called Chisel. Now, Chisel is a nice tool for basically trying out new Solidity code in a REPL environment. In fact, if you look at the help file here, there is this source instruction. So if we look at that, what this tells us is that this environment is really just a smart contract called REPL that has a single function called run. And so as we write code in this environment, so let's say I write uint256 a equals 1, then, and I have a look at the contract code again, you can see that it's just simply put this value into the run function, or this statement is now part of this contract. And the cool thing is we can look at the variables as if they're local variables inside our REPL environment. So this is a really cool tool. Highly recommend that you check this out and take a look at this. So what we want to do though in this example, in this exercise here, is just look at the ABI encode with signature function. And what we want to do is encode with signature the first, the example that we were using, so that we can get something like this back. So let's try, for example, balance of address, and we need to pass in the address, which is this part here, right? And we'll pass that in. And there we go. We got the data back. This is by calling ABI encode with signature. And one thing you might notice is it looks slightly different. So let's just take a look at this and paste it underneath this one here. And the difference is really the trailing zeros at the end, right? So you can see here the function signature is still 4 bytes, and then we got the same 32 bytes that follow that, but then we got all these trailing zeros. Really what that is it just basically makes the entire data, the call data, exactly 64 bytes, so that it fits into two 32-byte slots, if you like, or two 32-byte words. And so that's how the call data with ABI encode with signature works, is that it always returns these extra trailing zeros. But remember, as I said, Solidity would ignore these in this case, because it will take the first 4 bytes and say, this matches this signature, and then it would take that and say, well, I need the next 32 bytes, but I only need to take the address part of it, which is 20 bytes, and the rest I can discard. So that's a quick intro into ABI encoding and call data, and hopefully I showed you some new tooling there as well with Chisel and Cast, which come from the Foundry package here, right? So take a look at that if you haven't done so already. And so what we look at next is using this in YAWL. So as mentioned earlier, we've got call data which we can pass to a function or to a contract that will invoke a function based on the function signature and the data that's passed in it, if any. So I've got an example here, a basic example of a contract called another contract. It's got a function called getValue2222 or 222. Let me just clear this out here. I'm going to deploy this contract first of all, and then I'm going to deploy this other contract called YAWL call data. And this has one function in it called call another contract getValue2222. And it takes the address of the other contract, so the address of this contract will be passed in as a parameter here, and it's going to use assembly or YAWL to basically make a static call to this other function and in the other contract. And it uses a static call because it's just reading data from the blockchain. It's not going to change the state, so we can use a static call, which allows us to make this a view. Now, a static call takes the gas you want to forward to the transaction and the address of the contract, and then it takes the area in memory that you want to send as call data. So in this case, we only are interested to send the last part of this memory here because we stored the function signature of the call data, which is the function signature for getValue2222. And I can just show you that here. If we look at the cast of this, let me just get this out here. So cast is this value here, which represents the value that we've got here. And so I just stored that in memory slot 0, and that's why we just get this range here, because it's always going to be padded to the left. So the last 4 bytes will be the interesting value that we need, which is the value of the function signature. Now these last 2 parameters represent the area in memory where we want to write the results to. And we're just going to use the first 32 bytes of the scratch space, which is indeed the same area where we're storing the function signature. But after we've made this call, we don't really need this data anymore, so it's okay to overwrite it. Now, we use this pattern here to check that the success value returned from the static call is not 0. If it is 0, we revert because something went wrong. Otherwise, we just simply return the result, which is now already going to be written into this address space. So let's deploy the contract. We're going to deploy another contract first of all, and we're going to just check that we can call this function directly and it behaves as expected. Then we're going to deploy the YAWL call data contract, and we're going to use the address of the other contract as the input to the function call another contract getValue2222, and when we call that function we get back the value 222. And so what happened is that all of this code in here was executed, and we return that memory section here, which contained the value written to memory from the static call that went to this other contract on chain. So that's pretty cool, and that's how you make a static call to another contract using YAWL.